One of the world's greatest biochemical engineers has developed a fibre that will astound you.
It's roughly 5 times tougher than steel.
It's tougher than Kevlar, the material used for bulletproof vests.
The fibre is virtually indestructible.
The manufacturing process is a closely guarded secret, like the formula for Coca-Cola.
The military are looking for improved, lightweight, high-performance materials.
Labs in Britain, Germany and America claim to be on the verge of unlocking the secrets of this super material. Please welcome this extraordinary and ingenious engineer. At Oxford University, the Oxford Silk Group is a research lab dedicated to unravelling all the secrets of the phenomenal fibre produced by spiders. Spiders in Oxford live incredibly divergent lifestyles. On bridges, over canals, it's a windblown, catch-as-catch-can existence. But on the rooftop of the Oxford University Zoology Department, spiders receive 5-star accommodation, which includes all the fresh flies they can possibly eat.
We have about 100 to 150 spiders, which require nothing really more than a bit of hot temperature water and some flies once in a while. The spiders are fed in a free-range organic way where we release flies, and then if the flies get caught in the web, then the spiders are able to catch their own prey. One really interesting thing about spider silk is the fact that it's not already stored, reeled up like a fire hose. It's produced on demand, and it's stored inside the spider as a liquid gel. Now, this liquid gel is then carefully pulled through a specially shaped duct, and the act of just pulling it through this duct transforms it from this liquid gel into this hard, solid fibre.
Reproducing the liquid gel and replicating the process of transforming it into a fibre is the holy grail of spider silk research.
It's not just one type of material that you see here, it's actually 6 different types of silk created by different types of glands inside the spider. You have very strong dragline silks coming out from the centre, which act as the radial spokes and hold the whole web together. You then have very sticky and stretchy silks combined going all the way around, which are used to actually capture the flies when they fly into it. So if I put my fingers on this, you can just see how much this sticks to my fingers and moves, and it's a lot stretchier than the dragline silk.
After gently pinning this spider down, a fibre is pulled from its spinneret, and it can sometimes be spooled for hundreds of metres.
We know that silk is an extraordinary material. It has evolved over 400 million years, several times independently, because it's not just spiders that make silk, there's also silkworms, that has evolved over this long time period to make a material, a fibre, that is virtually indestructible.
The silk of silkworm cocoons is not as strong as spider silk. Farming spiders in large numbers for their silk hasn't worked. In close quarters, spiders eat each other.
Silk is truly a green material. This is in stark contrast to how we normally make our other high-performance fibres.
Kevlar is one of the highest performing synthetic fibres. It can literally stop a bullet. But manufacturing Kevlar is not an environmentally friendly process.
Kevlar, which requires concentrated sulfuric acid, 300 degrees, 400 atmospheres, is incredibly polluting. Spiders and silkworms can make a fibre that outperforms this man-made material using just leaves or flies as their starting material.
In the basement of the Oxford Silk Group is an arsenal of high-tech tools used to unlock the secrets of spider silk.
We really want to understand how nature makes these materials in order for us to try and copy it and improve our own.
For half a century, synthetic fibre production has been dependent on oil and petrochemicals. If or when the oil finally runs out, spider silk has the potential to be a revolutionary alternative. But before scientists can reproduce spider silk on an industrial scale, they must first understand it.
5, 4,
Research into spiders and their webs has even extended into outer space.
are running, all engines running. We have a lift.
In a 1974 NASA mission, 3 astronauts were joined by 2 spiders in a student experiment to see how weightlessness would affect the making of a spider web. There was some initial disorientation. But web building skills eventually adapted to weightlessness. However, scientists discovered that silk fibres produced in space did not have the strength of fibres produced on Earth. Back on Earth, the study of the physical properties of spider silk continues. In Germany, a university-affiliated lab called Biomat is exploring medical applications of spider silk.
The most important thing is to get a real clue about the mechanical properties of the fibers. There's one big drawback. The fibers are thinner than any synthetically made fiber. It took us almost 2 years to get a machine that really can measure such small forces. Now we can measure the forces of a single fiber.
Relative to weight, spider silk is 3 to 5 times stronger than steel.
Proteins are the building blocks of spider fibers and webs. So if you understand the molecules, then you can understand the rest of the system. What a spider has to do first in its gland is produce the proteins. This is done by specific cells. They produce the proteins and they secrete it, so they put it into the lumen of the gland. This is called the dope. And this is like the storage tank. So you have the proteins in water and they can sit there for weeks and nothing happens. So what the spider does actually, it pumps the dope into the so-called spinning duct. And the spinning duct is nothing else than actually a water-removing system. So this can be done chemically and actively by cells removing water, and it's actually a combination of both.
The chemical and physical process called spinning transforms liquid proteins into silk fibre with a new molecular structure and unique mechanical properties. This German lab and a commercial offshoot called AmSilk is not alone in chasing medical applications of spider silk. The Oxford Silk Group also has a commercial spin-off company hoping to market medical applications. Possibilities include artificial bones and ligaments, as well as superfine medical sutures. The success of these schemes still rests on developing the right genetic recipe for mass-producing spider silk proteins and finding a clever enough substitute for the natural spinning process.
The spinning introduces molecular alignment of the little strings of molecules in there, and folding of the strings of molecules. The molecules that fold very tightly back on themselves become like crystals. So they're hard. The soft bits are more like spaghetti, rather than really folded tightly like a Weetabix.
This combination of, we call it order and disorder, very stiff ordered molecules that give the stiffness of the material, and then the disordered molecules which are loose and flexible, which gives a toughness, and that's what gives silk its unique capability.
Understanding how to produce the feedstock has been very difficult, mainly because silk is a very large protein, and so our genetic manipulation methods and our biochemistry methods haven't quite yet got to the simple process of producing these silk proteins. A spider can do it easy peasy, yet for us to create it in the lab is very, very tricky.
Some initiatives to mass produce silk proteins have been audacious. Meet the spider goats. A Canadian biotech firm called Nexia, with help from a university lab in Wyoming, has produced a genetically modified breed of goats that produce spider silk proteins in their milk. It appeared to be a commercial breakthrough, with a fortune to be made if the protein could be spun into a tough, strong fibre.
People thought they have cracked the proteins and they know what it's all about.
The silk protein, the molecule, is very, very big. It's like a music song which is very, very melodic, but every now and then you have something in there that is not melodic. But to actually decipher it and then get all the bits of the melody in the right place is very, very difficult to do. So far, to my knowledge, nobody has succeeded to actually get the full protein, or the spider protein.
The spider goat fibres had only a fraction of the strength of the real thing. And the Nexia spider goat enterprise has been put on hold. Rather than using goats, the lab in Germany is using E. coli bacteria in the hope of commercial scale production of spider silk proteins.
We, on a computer, actually created genetic information based on the knowledge we have on the proteins. And now, of course, we can use the genetic information, put it in bacteria, and now they make actually silk proteins for us. We crack open the cells, and then actually we separate the silk proteins from the rest of E. coli, meaning we have then the silk solution that we need as a starting point for making fibers.
Whether bacteria are better than goats at creating spider proteins remains to be seen. And finding a cost-effective alternative to the natural spinning process is an ongoing challenge.
Since it's very hard to really mimic the natural spinning process, at least on the industrial scale, we can do that a bit in the lab, but not in a real process. We actually now tried to use the silk molecules in industrial available processes, and one of that is electrospinning. What you do is you just take your polymer solution, in this case it's a silk solution, and put it into a very huge electric field.
The solution gets zapped by a 30,000 volt charge.
Out of the solution, a fiber is formed. Just by electrostatic driving forces.
Electrospinning did not produce a tough, strong fibre. But the superfine network of fibres it does create may have medical applications as a biocompatible scaffold for human tissue growth and repair. What spiders do naturally is proving to be a tough act to follow on a commercial scale.
Nobody's given us raw material in bulk, a bucket, that we could just pour in the machine, that they're made somewhere by stirring something somewhere, and then they give it to us and we spin it. And so far nobody's given us the material.
Once we understand how this material is made, we can take this feedstock that we've managed to reproduce, put it through the right type of tube, and fingers crossed we'll get the spider silk at the end of it.
My gut feeling is we will find a few tricks to do it without actually fully understanding what we're doing first.